On April 30th, 2015, NASA deliberately flew a spacecraft into a planet at 3.9 kilometers per second. The impact crater it left on Mercury's surface is about 16 meters across. Mission controllers at Johns Hopkins had known for months it was coming. Messenger had burned through its fuel, and there was no way to keep it in orbit. So they used the last reserves to gather as much data as possible, then watched it go. The crash was not a failure. It was the end of 4 years of continuous observation, 4,104 orbits, over 270,000 images, and a data set that rewrote almost everything planetary scientists thought they knew about the closest planet to the Sun. Before Messenger, Mercury was considered a simple, dead world. A rock that formed early, lost its heat, and stopped being interesting a few billion years ago. The mission proved that picture was wrong on nearly every count. Mercury is the hardest planet in the solar system to reach. That sounds wrong. It's the closest to the Sun, just 77 million kilometers from Earth at its nearest. But proximity is not the same as accessibility. Getting a spacecraft into orbit around Mercury requires shedding an enormous amount of speed. Objects near the Sun move fast. Mercury orbits at 47 kilometers per second, compared to Earth's 30. A probe falling inward from Earth accelerates as it approaches the Sun, which means it arrives going far too fast to simply park in orbit. The solution is a 7-year multi-flyby trajectory. Messenger launched in August 2004 and spent the next 7 years doing gravity assist maneuvers. 1 flyby of Earth, 2 of Venus, 3 of Mercury itself, bleeding off speed with each pass before finally slipping into orbit in March 2011. The total flight path was 7.9 billion kilometers to travel 77 million. The only previous mission to Mercury was Mariner 10, which flew by 3 times between 1974 and 1975. It imaged about 45% of the surface and raised more questions than it answered. Mercury had a magnetic field, unexpected for a body thought to have a solid, inactive interior. The remaining 55% of the surface was a complete unknown. Messenger was built to fill that gap. The spacecraft carried 7 science instruments: cameras, spectrometers, an altimeter, a magnetometer, and a particle and plasma sensor. Its design included a large ceramic fabric sunshade, because at Mercury's distance from the Sun, solar intensity is up to 11 times what Earth receives, and without shielding, the instruments would have been destroyed before they could return a single reading. The first thing Messenger confirmed was that the magnetic field Mariner 10 detected was real and global, not a relic or an artifact. Mercury has an active, internally generated magnetic field, about 1% the strength of Earth's. For a planet this small, with a radius of just 2,439 kilometers, that should not be possible. Magnetic fields like this require a liquid outer core conducting electrical current, a dynamo. Mercury was supposed to be too small to maintain a molten interior this long after formation. The reason it does comes down to the core's size. Messenger's gravity measurements revealed something extraordinary. Mercury's iron core extends from the center to roughly 85% of the planet's radius. On Earth, the core takes up about 55%. Mercury is, in proportion, more iron than any other planet in the solar system, a dense metal ball wrapped in a thin, rocky shell. The leading explanation is a collision early in the solar system's history that stripped away most of the rocky mantle, leaving the core disproportionately large. A large iron core with sulfur mixed in has a lower melting point, which keeps it liquid, and the dynamo running longer than models predicted. Messenger also found that volcanic activity on Mercury was far more recent than expected. The smooth plains covering about 27% of the surface were formed by volcanic flooding, lava erupting across vast regions and burying older terrain. The timing, based on crater counts, put some of this activity at under 1 billion years ago. For a planet thought to have gone geologically dead within its first billion years of existence, that is a significant revision. Then there was the surface chemistry. The spectrometers found high concentrations of sulfur, potassium, and sodium, elements that evaporate at relatively low temperatures. Standard models of Mercury's formation, which involved the planet forming very close to the sun and baking at high temperatures, predicted these volatile elements would have been driven off long ago. They weren't. The chemistry implies either a different formation history or a more complex early solar system than the models account for. The most striking finding was at the poles. Mercury's axis is tilted less than 0.03 degrees, essentially zero. This means the floors of craters near the poles never see sunlight. Permanently shadowed, they maintain temperatures as low as -180 degrees Celsius, even as the sunlit surface reaches 430 degrees Celsius just a few hundred kilometers away. Messenger's neutron spectrometer detected hydrogen concentrated in these regions. Combined with radar data from Earth-based observatories, the conclusion was clear: water ice, sitting in the dark on the planet closest to the sun. Mercury is not the obvious candidate for a future outpost. The surface temperature swings from 430 Celsius on the day side to -180 at night, a range of over 600 degrees, the largest of any planet in the solar system. A solar day on Mercury lasts 176 Earth days. The magnetic field is too weak to deflect solar radiation the way Earth's does. And getting there, as Messenger's 7-year journey illustrated, is genuinely difficult. But the polar craters change the equation somewhat. Permanently shadowed crater floors with water ice and stable cold temperatures sit adjacent to crater rims in near-continuous sunlight. A structure built on a rim would have uninterrupted solar power, potentially the most energy-dense solar environment accessible to humans, given Mercury's proximity to the sun. Solar panels there would generate roughly 6 to 10 times more power per square meter than the same panels in Earth orbit. The ice provides both water and, through electrolysis, oxygen. The crater walls offer shielding from radiation and micrometeorite impacts. The combination of abundant energy and shielded cold storage in one location is unusual in the inner solar system. It does not make Mercury easy, but it makes it less impossible than it appears at first. Messenger answered the major mapping questions but left the deep structural ones open. The size of the core is established. Why it is so large is not. The giant impact hypothesis, a collision that blew off most of the mantle early in Mercury's history, is the leading model, but it has not been proven. The alternative, that Mercury formed from material already depleted in silicates close to the sun, runs into the volatile chemistry problem. If it formed in such a hot environment, the potassium and sulfur should not be there. The magnetic field structure is also strange. It is offset. The center of the field is displaced about 480 kilometers north of the planet's geographic center. No other planet in the solar system shows this kind of asymmetry. The cause is unknown. The volcanic timeline needs more precision. Messenger's crater counting method gives estimates with significant uncertainty. Whether Mercury was volcanically active as recently as 300 million years ago or closer to 1 billion makes a large difference for models of how small rocky planets cool. The follow-up mission is already flying. Bepi-Colombo, a joint ESA-JAXA spacecraft, launched in 2018 and is set to enter Mercury orbit in 2026. It carries more capable instruments than Messenger and will address several of these gaps directly. The answers, when they come, will either confirm what Messenger suggested or force another revision. Mercury spent decades as the solar system's afterthought. Too hot, too close, too hard to reach, too small to be interesting. Mariner 10 flew past 3 times and left half the planet unimaged. For 33 years after that, no spacecraft went back. Messenger spent 4 years in orbit, mapped 100% of the surface, and found a planet with an oversized iron core still generating a magnetic field, volcanic history extending into the recent past by geological standards, surface chemistry that contradicts formation models, and water ice sitting in permanent shadow a few hundred kilometers from the hottest surface in the inner solar system. The picture that emerged is of a planet that formed differently, evolved differently, and preserved information differently than anything the standard models predicted. It is the closest planet to the sun, and in some ways, the least understood. Bepi-Colombo will add resolution, but the framework, the realization that Mercury is genuinely strange, belongs to Messenger. The spacecraft is still there, somewhere under the crater it made when it hit, a 500-kilogram piece of engineering that traveled 7.9 billion kilometers to teach us that the obvious answer is usually wrong.